Okay, get ready to have your mind bent a little. We're about to dive into this wild idea called single-point theory, and it suggests that the universe, our entire reality, has a hidden rule, one we've been missing all along.
So it all starts with this simple but kind of spooky thought. What if, underneath everything we know about physics, all the equations, all the theories, the universe is playing by a secret rule, a rule that's been right under our noses but totally invisible?
And here's the kicker. You know that line we draw? The one separating what we know from what we don't? The boundary where we hunt for new physics? Well, what if that line isn't a line at all? What if it's a moving target? And the crazier part? The harder you chase it, the faster it runs away.
Right, so to get our heads around this, we've got to first understand this hidden rule and what's up with the strange shifting wall it seems to create.
Okay, so in normal everyday physics, it's pretty straightforward. Think of it like this. Every experiment has a limit to how clearly it can see. It's like a resolution limit. This creates what physicists call a wall of falsification. If your new shiny theory makes a prediction we can see on our side of the wall, great, we can test it. But if its predictions are beyond that wall, well, they just stay hidden. We can't touch them.
But, and this is the big but, this is where single-point theory just flips the whole table over. It says that wall isn't a wall at all. It's not fixed, it's dynamic. Imagine trying to run a race where the finish line literally runs away from you. And the faster you run, the faster it moves. That's the problem we're facing.
And look, this isn't just some philosophical musing. We've got data. Check this out. When physicists use a pretty low-energy probe, think of it as a gentle tap. The wall where new physics could be hiding is at about 89 MeV. Okay, reasonable. But then, they increase the probe's energy by just 3 times, and you'd expect the wall to maybe move out by 3 times, right? Nope. It leaps out by a factor of 5, all the way to over 430 MeV. That is not normal. Something really weird is happening.
What this points to is a really strange mathematical relationship, what we call a scaling law. In plain English, it means the boundary for new physics runs away from us faster than we can chase it. It's exactly like trying to climb a wall that gets steeper and taller the higher up you go. It's a cosmic game of keep away. So this gives us this amazing concept of vacuum stiffness. It's like this. When you poke reality gently, with low energy, the vacuum of space seems soft, pliable. It feels like new physics could be hiding just around the corner. But if you hit it hard with a high-energy probe, reality suddenly tenses up. It becomes incredibly stiff, like it's bracing for impact, and pushes that wall for new discoveries way, way out. I mean, how weird is that? It's like pushing on a door, and the harder you push, the heavier the door gets. It just doesn't make sense. So the real question is, what kind of universe does that? What theory could possibly explain a reality that seems to actively fight back against being discovered? Well, you might think the answer comes from some giant particle accelerator or a supercomputer, but you'd be wrong. The answer, or at least a potential answer, comes from a really simple, almost philosophical question about the very beginning of everything. So the guy who came up with this, Damon Higgins, he didn't start with a blackboard full of math. He started with a question, a what if. He asked, what if the Big Bang didn't bang? What if that initial infinitely small point wasn't obliterated in an explosion, but instead just started moving? And that right there, that is the core, the absolute heart of single-point theory, or SPT. The idea is that reality isn't a static thing, it's a dynamic process. The entire universe is being constantly generated, painted into existence by a single point moving in a loop at the fastest possible speed, the Planck frequency. We're talking about 10 to the power of 43 times per second. It's like our reality is a movie being refreshed at an impossible frame rate. Okay, so if reality is just one tiny point zipping around, how on earth does that create, well, everything? Stars, galaxies, us? What does that process actually look like? Let's try an analogy. Instead of empty space, imagine the universe is this huge, turbulent ocean. Let's call it the process field. And at any given location in this ocean, there are 2 things that matter. Amplitude, which is kind of like the height of the wave, that's the local energy, and phase, which is its rhythm, its timing relative to everything around it. Now, if you buy into this model, then you have to totally rethink what a particle is. An electron, for instance, it's not a little solid marble anymore, not even close. Now, in this picture, particles are more like stable whirlpools, little vortices in that cosmic ocean. They're these self-sustaining, resonant patterns of energy and rhythm that have found a way to persist. This is a huge shift in thinking. Particles aren't little things floating in the universe, they are patterns of the universe itself.
Okay, deep breath. This is where it all connects. How does this amazing, almost poetic idea of particles as whirlpools explain that weird, stubborn scaling law we started with? How do we get from a cosmic ocean to a wall that runs away from us? It all comes down to how this process field reacts when we poke it in our experiments. A low-energy probe is like dipping your toe in the water, a gentle ripple. The field basically yawns. But a high-energy probe, that's like a cannonball, a violent jolt. You're trying to create a really steep change in the field's energy, and the field, it pushes back, it resists, it stiffens up to handle the shock.
And that resistance, that pushback is exactly what our detectors measure. It shows up as a tiny little deviation from the energy we expect to see. And where does it come from? Well, it's a combination of two key things.
First, you have the steepness of the gradient. Basically, how hard are you trying to jolt the field? And second, and this is the crucial part, you have something the theory calls the field's lag penalty. Because reality is a process, it can't just instantly react. Think about trying to turn a massive cruise ship. It doesn't happen on a dime. There's a lag. And the faster and sharper you try to turn it, the steeper your gradient, the more that lag fights you. That penalty gets huge really fast.
And here is the absolute mic drop moment. When you do the math, when you calculate how that lag penalty would make the wall seem to move to hide its true nature from us, the theory doesn't just say it moves fast. It makes an exact prediction. It spits out a precise exponent for that scaling law, 1.5. 1.5. This number isn't just fudged to fit the data. It falls right out of the fundamental idea that reality is a process with a built-in lag. It's a pure prediction. So, you see, this isn't just some neat sci-fi story. It's actual testable science. Because SPT doesn't just explain old data. It makes brand new predictions about things we can go out and measure. It puts its head on the chopping block, which is exactly what a real scientific theory has to do.
And here are a few of those battlegrounds. The theory predicts, for example, these tiny little frequency shifts in special kinds of atoms, shifts the standard model says shouldn't be there. It predicts that a certain measurement in heavy ions will scale differently than we expect. It even makes a prediction for cosmology, saying that high-energy light from gamma-ray bursts should redshift just a tiny bit less than low-energy light. These are all clear, unambiguous tests. If the experiments don't see these effects, if the standard model holds up, then single-point theory is wrong, plain and simple.
And that leaves us with one last, really deep thought to chew on. If this theory is even close to right, if reality is just this single, immense interference pattern, and if particles are just stable whirlpools in that pattern, then what does that make us? I mean, we're made of those particles, right? It kind of suggests that we aren't just observers looking at the universe from the outside. We are the universe. We're just one of its most complex, self-aware, resonant patterns trying to figure itself out.